Professor Colangelo from University of Bern is a famous theoretician who in particular make a very reasonable contribution to the studies of very exciting property of today's modern physics, fundamental physics, that is the G-2 charged electrons, in particular muon. So probably I would like to ask you in 2 words explain why G-2 of muon and also electron are so important.
Yes, so these quantities, which are anomalies, they are called anomalous magnetic moments because it's a small deviation from 2, which is the value predicted by Dirac's theory. And then the deviation is what you were mentioning now, alpha divided by 2 pi, is calculated by Schwinger,
yeah, I'm sorry.
which is a 1 per mil deviation from 2. And this deviation from 2 has been measured with incredible accuracy for the electron parts per billion, few parts per billion, and for the muon now half part per million. And which means that it's something which one can compare to theoretical calculation at very high accuracy. And as is well known, you can discover new phenomena in physics, either going to very large energies, as is done at LHC, or going to very high precision. And then you discover small phenomena which give only tiny contributions to known observables. And that's the case. In fact, although the precision for the electronic G-2 measurement is much higher, the muon is more interesting because due to its higher mass, the muon observable is more sensitive to
physics on small scale.
Yeah, to physics to new physics contributions. And so for the muon, there is now since 15, 20 years a discrepancy with the standard model calculation, which despite many calculations, scrutiny from all possible sides has stayed. Nobody could make it go away. And so now there is a new experiment planned which could increase the precision of the experimental measurement, and so this could lead to a very serious discrepancy which would call for the existence of new physics, which is what we are all looking for.
Yeah, that will be some indirect indication.
Absolutely, indirect. If you establish that there is this difference, then the question remains, what is it due to? So for that, then we have to go to LHC or other machines which would allow us to see these particles, these new particles.
Would you please just say a few words about your personal contribution to the theory of calculations?
Yes. So since about 5 years, with a group of young theoreticians, all very bright, let me mention them: Martin Hoferichter, who is now in Seattle, Peter Stoffer, who is now in San Diego, and Massimiliano Procura, who is now in Vienna. So we have tried for the first time to derive a dispersion relation for the so-called hadronic light-by-light contribution to G-2. This is a next to leading order contribution from hadrons to G-2. The leading one is, of course, much more important, is hadronic vacuum polarization. And that is calculated to very high precision because since the 60s, it's known how to apply dispersion theory to this one. And thanks to this dispersion theory, you can relate this contribution to something measurable. In that case, is E plus E minus 2 hadrons. For hadronic light by light is more complicated, but the observables which matter there are the transition form factor of the pion, which can be measured, and in fact measured quite well. And then anything gamma-gamma with virtual photon cross-section in 2 hadrons. These are the observables which, if you know them, you can calculate this contribution well.
Okay, well, thank you very much. And in fact, you have mentioned in your talk that or probably your colleagues who follow you with the description of two experiments you just mentioned on the measurements on G-2, that if the central value, experimental value, will be fixed as it now,
yes.
So the deviation between your theory and the new values will be about 7.
Exactly.
That's so it will be like
that would be
like
a very
discovery.
that would be a very exciting
yeah.
scenario for the future.
Well, thank you very much.
Thank you very much.